Now, we live in interesting times, right? So the AI and machine learning hype is all-time high. And even at the scientific outlets, you see this, news titles. So here on the left, the Royal Society of Chemistry wanted synthetic chemists, human need not apply, chemical engineering use, right, or the smartish machines. So just to maybe, induce some discussions after the talk. So I'd like to start with thought-provoking quote attributed to Derek Law, who wrote the blog to the Science Translational Medicine. So Derek said, it is not that machines are going to replace chemists, it is that chemists who use machine will replace those that do not, right? Instead of chemists, here can be truck drivers, taxi drivers, and other different professions. Now, and I think in the age of machine learning AI, you might appreciate that actually chemists been fascinated with this question: can a computer learn chemistry? Right? Given this formula, can I predict reactivity, biological properties, spectra, and so forth? And what I'm going to talk about, I don't know, backgrounds on the people audience, kind of to put everyone on the same kind of baseline. I'll talk a little bit what's called the supervised machine learning framework, and it's essentially a methods, techniques from machine learning when you deal with labeled examples. Imagine materials, energy, materials properties, patient and disease, things like that. So you have the tuples of examples from historical data. And you estimate, essentially, you find this magic function F that connects, features of those objects with their output or, useful properties, right? And you minimize essentially the error using the training data. But then you want to test it and, and kind of perspective discover and apply it for never seen before examples. Kind of useful examples, for example, if you run a reaction, you want to do solvent selection, right? So you want to maybe find a function that, recommends you a particular solvent to run your reactions. A lot of drug discovery done is connect molecular structure into biological property, things like binding affinity and inhibition. Or, for example, designing a catalyst for the next process. So all of that, looking to fit this, function as connect structure with some useful properties. So hence, how this can help in solving, quantum mechanics and address the problem of time-independent Schrodinger equation. Now, so this is the only formula I have. So this is the time-independent Schrodinger equation. Now, if you look from this formula, from the point of view of machine learning as a data scientist, so my ground state energy and this whole equation can be rearranged as exactly supervised regression problem where energy is magic function F from molecular coordinates. And then you essentially fit the functions that would approximate your solution of Schrodinger equation. In our lab, we use neural networks. So essentially what we do, you take molecular structure, you shove it into the neural network, you predict energy. The beauty of neural networks, they're fully differentiable. So you can backpropagate and compute gradients, and therefore you can now have forces. You can backpropagate twice, and now you have a matrix of the Hessian. And therefore you can do all type of quantum mechanical simulations for molecules, materials, and other things. And therefore it's all boils down, in my opinion, kind of representation of the structure, right? So molecules, materials are quantum, therefore they interact by the fundamental forces of interaction. So this is how molecule view to another molecule, essentially showing you the potential of, electrostatic surface. Usually we as a chemist kind of look on molecules at the 2D sketches, so you show the structure of the molecule. But for the computer, molecules and materials are typically represented as a graph, where you have, edges and the vertices of those graphs. So the edge would be a chemical bond, and the vertex would be the corresponding atoms, which essentially resulted in the whole zoo of different either graph-based or more generally what's called the 3D point cloud models. So point cloud would be the points, atoms in three-dimensional or high-dimensional space. And therefore, you see this, hundreds probably different methods, things like graph convolutional method, direct acyclic graph, message passing, view models, tensor network, and so forth. So now Oleh, we responsible for a couple of these architectures, and essentially I'll show you, a couple of examples of those neural networks, and therefore why and how this is all useful. So if you're interested to do simulation for a large system, you're forced with the dilemma, right? If I have 1 million atoms, I may not necessarily be able to solve Schrodinger equation, and therefore you have to use something like empirical potentials or a force fields to do a simulation, right? So this is very crude approximation, but it can scale for larger systems. And therefore, the typical dilemma, what we have, in this plot, so x-axis would be some kind of metric of scaling, and would be number of particles or number of electrons, and y-axis would be, some kind of metric of accuracy. So if you're interested to run very large simulation, things about protein, simulate grain boundaries, things like that, you're kind of stuck in the realm of these empirical potentials because they're linear scaling, and you can run very large simulations. Now, if the quantum effects are important, you may have to climb this ladder. Things like using semi-empirical method, density functional theory, or in my realm of organic molecules, so coupled cluster theory would what's called the gold standard. And therefore, the promise of this machine learning potentials that if you train your ML model, so for example, on a density functional theory data, you can essentially made a method that is favorable scaling, so a neural network are linearly scaling, and you can approach the accuracy of reference theory, so for example, density function theory. And therefore, you have this 4 or 5 orders of magnitude speed up for those simulations. So the first examples of what I call this transferable neural network force field for organic molecules was called the ANI architecture. In our work, we specifically look in small organic drug-like molecules, but many other methods exist. It's been parameterized for materials as well. If you heard about SOAP-GAP, Baller-Parinella neural networks, they all kind of similar, looking to solve more or less the same task. An idea of the neural network, so what you take your molecular structure, and every atom inside the molecule or a material would be characterized by the spherical environment, which we call the symmetry function, to a certain cutoff radio. And this spherical environment encodes this atomic neighborhood, essentially all your neighbors until the cutoff. And what essentially happening, your neural network zoom in one environment at a time, and the total energy of the system would be sum of these atomic environments. And therefore, approach is very simplistic. You have purely geometrical descriptors. You pass it, you featureize, compute the symmetry functions, what we call radial and angular symmetry function, pass in very simple neural network, multi-layer perceptron, compute this fictitious local energy, sum them up, and get total energy. And so this is how to train, how to do simulation. Essentially, it's a computer code with pre-trained weight, which you plug into your favorite simulation package. Can be WASP, can be LUMS, or any type of package. And then it provides you energy and forces, or properties if it's parameterized. So essentially, we maintain, the fully open source ecosystem called Torch ANI. So we use PyTorch framework. Essentially, with the current ANI architecture, we parameterize 7 biogenic elements. So this is, again, mostly focused on kind of drug discovery applications. But with more advanced architectures, we now have 14, 15, elements. For computational chemists in the audience, we have 2 levels of theory. So you have a particular hybrid DFT functional with a decent basis set. And we have a parameterization to, DLPNO linear scaled coupled cluster for very accurate thermochemistry. So essentially what it allows you to do all kind of typical applications. geometry minimization, properties, molecular dynamics, your favorite ensemble. You can do thermochemistry, harmonic, quasi-harmonic approximations. For molecules, we build tools for conformational search in the gas phase and continuum dielectric for the solvent effect, implementation of periodic boundary condition, and the main decomposition method. So you run on multiple GPUs, and then analytic, you can compute stress tensors and the optimization of the cells. So essentially, it revolutionized how a lot of people think about obtaining structure of small organic molecules. Essentially, it provides you extremely accurate method to compute three-dimensional structure of the molecules, compute potential energy surface of the molecules, finding conformers, ranking by energy, and very good accuracy for gas phase thermochemistry. Again, references here, and I will pass the slide deck so you'll have access all to these references. Now, I do not work for, with a lot of material science application, but Justin Smith, who was the first author on the ANI paper, after graduated as a very talented graduate student at the time, went to Los Alamos National Lab and eventually became a staff scientist there. So so in that applications, what he shows that using the same architecture, he was able to train machine learning potential for aluminum, for example. And they done very interesting multi-million atom simulation of shock wave propagation. So when induce the shock wave and see, phase transition inside the aluminum, how shock wave essentially propagates, and look for some interesting, clustering of the atoms, what the mechanisms grow of this, all of that. And therefore, again, so that particular architecture is not only applicable for molecules, but can be extended for materials as well. And overall, again, as the Department of Energy lab, they've done a lot of development for the machine learning potential especially for F elements. Now, in parallel, we continue work with Justin, and our latest development, published early this year, is making a fully reactive ML potential for CHNO chemistry, right? If you ever fit things like empirical reactive potential, something like ReactFF or Ariba, this is really, really hard problem. So what we've done essentially try to use ideas, what's called the active learning and idea of the nanoreactor to train this essentially transferable reactive potentials. What we did essentially, stuck into small organic molecules into the small periodic box and induce high temperature molecular dynamic simulation, dynamically varying temperature and the volume. So essentially, you cook molecules and induce reactions, and you cook them and you look for uncertainties and stop dynamics, run QM calculation, update your neural network, and again details in this reference. But what it allows us essentially to do is to make this reactive potential transferable to multiple different phenomena. I'll show you a couple of applications, but in the paper we actually had to do and show 5: nucleation of the carbon, formation of the graphene, various type of combustion and applications, and early life, for example, like a Urey-Miller experiment. So one example, what we're very surprised that despite the fact that potential was trained for small organic molecules and maybe a little bit larger cluster of atoms in the training, we were able to reproduce, decently good phase diagram for carbon. So for example, if you run a simulation, high density carbon, medium density, or low density carbon, and do, high temperature simulations, you end up that, this carbon, essentially nucleates and go into the diamond cubic lattice and the high density, into graphite layers, medium density. In a low density regime, you get this fullerene kind of onion-like structures. You can also describe phonons for the crystal structures and a decent kind of lattice constant for different types of carbon allotropes. Now, in parallel, again, you can look for more interesting application in, kind of in kinetics. So, for example, oxidation of graphite, of the graphene. And there is a known experiment and other simulation that depending on the, if you do simulation of a mixture of acetylene with oxygen, depending on the ratio, the amount and type of this carbonaceous, compounds would vary. And it makes sense because more oxygen you have, higher oxidation you would observe. So we were able to run the simulations for different, ratios between acetylene and oxygen, and essentially, be able to predict, observed ratio for different concentrations and kind of verify the experiment. And finally, you can also have fun, to do, combustion chemistry, put hydrocarbons, in an oxygen and see how it burns, see formation of the products and so forth. And therefore, accuracy of this potential was essentially consistent with ab initio simulation and also specifically fit bespoke ML potential for these reactions. With that, so again, 2017, ANI framework, very simple idea, but many powerful, impactful applications. Now we'll fast forward to 2024, and I'll skip several different intermediate architectures, but kind of I think about as making, playing with the Lego blocks and designing the architecture as essentially combining these Lego blocks and, designing a neural network architecture. So what we come up this year is now second generation atoms and molecules MN potentials. So it's been trained to very large data set of hybrid DFT calculation, about 20 million data points, sampled from different various sources. So it includes all non-metal elements. Now, in contrast to any neural network, it works for neutral and charged species. So you can encode the charge and this molecular charge and the spin states. Now, in addition to organic molecules, it works also for elemental organic molecules, things like molecules with boron, silicon, selenium, and so forth. Now, if you're curious for architecture, now this is the architecture, and it's much more complex. Now, in addition to be purely geometrical descriptor, now conditional neural network to total molecular charge and a multiplicity if it's a open shell system. So you can describe radicals, spin states, and here I think where you might have interest in that as well. Now, in the ANI architecture, our descriptor was purely, derived, symmetry functions by hand. Now, every atom inside the AMNet is described by learnable representation, a vector, what we call embeddings. And that vector is learned during the training. Now, since we have the total molecular charge and multiplicity, we have this interesting block, which we call neural spin or charge equilibration, if it's a closed shell systems, that assign spin charges or charges per atom. And this is, I think, where it might be interested and applicable to a system. If you're interested in quantum materials, you can describe magnetic effects. You can describe, you can put, instead of the scalar, you can put a vector or tensor properties per atom and describe more interesting, effects for quantum systems. Now, so the total energy of the system would now consist from 3 steps. Now, neural network, essentially describe the kind of local and semi-local part. As in, conventional DFT, we use dispersion. And since this is an analytical term, there's no need to learn it. And since now we have access to partial atomic charges, we can plug it in and explicitly compute electrostatics term. So it essentially shows you kind of interplay between kind of pure data-driven machine learning methods plus, physics-based term. Again, I talk a little bit about how neural spin equilibration works, show you kind of cartoon representation, why it's important. what essentially it allows us to reproduce this non-local effects. So for example, if you take this conjugated organic molecule, you either attach or detach electron from it. So what DFT would tells you in terms of the spin density, you see formation of this spin density wave-like behavior with plus and minus phases. Now, if you use just purely geometric descriptor, that effect cannot be described, and neural network, not only ours, but any purely geometrical descriptor-based neural network would get you qualitatively wrong answer, and all charges will have the same phase. Now, with this spin and charge equilibration, an idea what's called a message passing, you update those embeddings inside the neural network, and you can see formation of the spin wave-like behavior, and overall, you can have a proper description for this non-local effects. Again, if you're interested, there's a reference to see how it works. Now, what was also interesting that, and this is another directions, what's called the differentiable physics, is that, for example, in chemistry, there is an extension for density functional theory called conceptual DFT, which essentially connects partial derivatives of the energy with respect to the total number of electrons. This is the kind of the total quantities, but there are also condensed properties, per atom. And therefore, since neural network is fully differentiable, now we can fully bypass QM calculations and essentially extract those first and second derivatives directly from neural network, and therefore compute all those quantities that can now be applied for downstream, task of prediction reactivity and other property calculations. Just a little example. So again, the MNet2 is linear scaling in the regime of the larger system. So I'll show you an example. So for 100,000 atoms, essentially getting energy and forces, it's about half a second. So it is slower than a traditional force fields, but it is much, much larger than DFT. So for example, here on the left, also comparison with the popular quote from the Stefan Grimme lab from Bonn, GFN2XTB and GFNFF. Again, MNet, couple of, about 10 times faster, and therefore you can do simulations. For example, compute energies conformers within a few seconds on a GPU. And finally, I kind of think about this MNet2 as a baseline model, as a foundation model for a variety of different applications. So we parameterize some of the elements, not all of them, but you can start now from this pre-trained model and extend it for a variety of different tasks. So for example, combined with statistical thermodynamics and salvation model used in kind of hybrid machine learning and molecular mechanics calculation. I'll show one quick example for reactions and maybe also use a generative model and so forth. So what we work right now is, help to solve one of the long-standing problems in chemistry, localizing transition states, finding the, heights of the barriers of the reactions, and essentially, kind of quantifying chemical reactions. So one of the example of including the first metal element is not that we cannot describe the metals, but kind of directions of my work is typically in organic chemistry. So palladium is the first metal we extended to, and this is very important for what's called the homogeneous catalysis, where palladium organic complexes, used in organic synthesis and pharmaceutical chemistry to do various types of cross-coupling reaction, carbon-carbon, carbon-nitrogen reactions. And with that model, for example, again, you can obtain geometries, energy, and do rapid profiling of the multi-step mechanism of palladium catalyzed reactions. And finally, since we have a mean to describe, the spin states, you can extend not only from closed-shell systems, but also for open-shell systems. And I think, again, this is where that might pique your interest. So this is an example of radical decomposition reaction. It's collaboration with actually BASF, a company in Germany. where this initiation of this radical reactions goes from what's called the singlet state to the triplet state. And so what you see lines here is, comparison of this reaction profiling with DFT versus AIMNet. And essentially what you see, you start from a singlet state in blue, but then as this reaction goes, you see formation of two radicals, and therefore you end up in a triplet state. And this is where it crosses, and essentially reaction switches the potential energy surface and goes into the triplet states. And therefore, you, again, for the first time, you can allow the simulation be done with the neural network. With that, let me stop here and kind of leave you a bunch of the links, all our codes on GitHub. Our neural network have plugins to a variety of different packages, hopefully some of your favorites. And most of our data is also available. And therefore, if you find it useful, please use it. With that, thank you very much, and happy to answer any questions.
Thank you very much for this interesting talk, which is open for discussion. Questions from the audience or from the online audience? So maybe I can start. I have a rather technical question. So you show that you can deal with molecules that have very different size, but on the technical side, I think it's challenging to deal with the molecules of variable size. So you have to for encoding the crystal structure as a vector, you need to fix the length of the vector typically in ML approaches. So how do you solve this problem?
So the descriptor vector is actually consistent. There is nothing special here. We have periodic boundary. You can work with the crystal cell. And I think if I go to this slide, I think it will be best described, right? What essentially neural networks see is this constant size representation vector. And then depending on the size of the system, you'll have different number of these things. But again, the framework handles for that. But your descriptor size is always consistent. It's fixed dimensionality of this atomic environment. And then essentially you just, for simplicity, you present one by one, and it doesn't matter your system is 10 atoms or 10 million atoms. Mm-hmm. Your descriptor is always fixed. And if you have periodic boundary condition, it correctly accounts for, the symmetries and, the central cell and all other cells.
Yeah, thank you. More questions?
Hello, Alexandr Isayev. Just wanted to ask, when you shown this seven or something elements, yeah, which you said they are solved for these elements, what does it mean? What do you have? This for each you have this pre-trained network, or?
Yes, so it is pre-trained. So the beauty of that, again, kind of because of time, I kind of skip in. We pre-train this neural network and the weights available. So if you have this element parameterized and your system of, because there's no magic here, right? If your system kind of in the realm of applicability of this neural network, you grab it in and you do your simulation.
If you want to calculate, so it is for molecules, right? But this means that you can calculate them, predict the molecules with these elements included.
Yes. So any combination, any size of the molecules with that elements, plus there is a caveat, right? So for example, this specific neural network, it's for neutral molecules. Then this neural network from this paper, it worked for extended systems for, graphene, carbonaceous materials, molecules in essentially liquids, high temperature simulation. This will work for materials, but again, this one for parameterized for only 4 elements.
Yeah, just my naive expectation that you should to have pre-trained networks, let's say, for pairs of elements, not for elements or something like. If you want,
it learns well. It's easier to think about number of elements than pairs. I absolutely agree. So neural network should see what elements form what kind of bonding, right? Carbon, oxygen, oxygen, nitrogen, and so forth. But for simplicity, I'm thinking about, and also for a smaller number, right? Because the pairwise would have, this scale, and more and more elements you have essentially, exponential number of chemical bonds. But absolutely agree. Yes.
Okay.
Thank you for the great talk, Volodymyr Bezguba. I wanted to ask about input data. Like you have specific one, like in ANI you had only two basically sets, right? And here you had extra information, but it doesn't incorporate anything like about graph structure if you encode it, even if it's just for molecules, like in graph neural networks, nothing from that, right?
Yes. So basically, that's idea of we don't use topology. What you essentially do when you run QM calculation, I don't know, run WASP, right? You specify the atoms inside the cell and maybe parameters, charge and multiplicity of your system. That's exactly what we use, right? So we don't use specific topology. So we don't draw explicit chemical bond. And the neural network learns from the spatial positions between the atoms.
Topology arises from that.
Yes. So it inference and learn what it is to be chemical bond and what it takes to break it.
I see, thank you. And one more short question. You mentioned active learning. Does it mean that for your second generation of architecture, does it mean that instead of scalar there, if you use, for example, some vector for magnetization or other physical characteristics, you can just like add it quickly to the network, or you need to retrain it completely? Like how deep is it in architecture?
Great question. So at this point, we use scalar property here, right, as the charge, because it's just one number. Now, you can use vector property here. You can use tensor, and then the neural network get a little bit more complicated. You need to retrain. If you change the architecture, you need to retrain. Is it with our data or maybe with your data? Mm-hmm. So that would require retraining. But again, the most time takes to obtain the reference QM data. Then retraining takes probably like 2 days or so.
And very last, very short question. How many elements do you have for this architecture train?
So at this point, we have 14 non-metal plus extension to palladium. So it's 15.
Thank you.
So I think we have to move on. Alexander, thank you very much for joining in.
Thank you. And have fun.
The next talk is given by Oleh Feia, who will show his results on implementation of structure predictions with atomistic simulation and environment library. Right. Oops.
Oh, sorry. Stop it. Change it.
Even forward backwards.
But the keyboard should always work.
Okay. Thank you very much for this opportunity to give this talk, and I'm very glad to do it in Dresden. Here I will tell you about our crystal prediction methodology, which we made with my student in Kyiv Academic University with Bogdan Semeniuk. So it was his diploma project, and Olexandr Isayev, who made previous talk, was referred to this to the diploma. And in future, we have for the closest future, we have some plans to collaborate and to add this methodology to Alexander's machine learning potentials. So I will give you words about computational materials design, and this is the thing which also Alexander makes, and I'm working in this field. So it means that we are going from composition. Composition can be some names of elements, chemical elements. Then we somehow from this composition we get the structure, and from the structure we get we create some properties. And we can do it in a lot of ways. We can use machine learning some potentials. We can use density functional theory. It is now it is the most popular way to calculate these properties. But as you see, machine learning also become very popular. And also we can use some evolutionary approach to get from composition the structure, and then with DFT calculate the properties. We can do it with a lot of programs of FPLO, which is developed in Dresden, VASP, Quantum Espresso. And in this step, from structure to properties, people usually use density functional theory. And few words about it. So it's based on Hohenberg-Kohn theorems and on Kohn-Sham equations. So Hohenberg-Kohn theorems give us few rather simple statements, but the statements was not so obvious, and it was Nobel Prize for Walter Kohn in 1998 for this statement. So he told us that all properties are determined by electronic density of some crystal, and then the energy function of the ground state is determined by electronic density of the ground state, and we don't have any other energy functional which follows the same electronic density. And Kohn-Sham equations just give us some useful block scheme how to calculate, how to implement it in some computer programs and use it to calculations. And this theory, it was, it's still, I think it's still the most popular theory to calculate properties, crystal properties. It began its rise in 1990s with when some computer powers became accessible, available, and now it gave a lot of, I think, like thousands paper each year uses this property, this theory. And another step from composition to structure. So here we can use some machine learning methods. We can use some genetic and evolutionary approaches. Here you see some programs. I have experience with most of these programs. And it's some problems how we can from the composition get crystal structure or a lot of crystal structures, or we can explore some system with numerous crystal structures. All these methods, they have the core idea, the core algorithm. So it's like this genetic or evolution algorithm. How it looks like. We initiate the problem, so we type that we want some, we want to explore some chemical system. Then we initialize the first population of the system. We create some structures. Then we create some fitness function. We can calculate it with DFT. We can calculate it with machine learning, and then we check some conditions. So, for example, we create this energy, then we check, then we take the best structures, we apply on them some algorithms, and we create next population. And we will do this till our condition will be fulfilled. So for example, for 10 or for 20 populations, the best structure will not be changed. So if it happens, then we say that maybe we have found the best structure in this system. So this is the main idea of all these methods. There are some also machine learning based methods. So this is genetic algorithms. This is machine learning based methods. This is paper of 2024, very fresh. And the authors of these methods, they used the core ideas of evolutionary approach, but they used machine learning to calculate the energy of these crystals. So they don't use DFT because DFT, as you saw from previous talk, it is rather it is very slow. They used machine learning. And they got DFT. They got the results of energies, which is approximately like DFT. So they trained this their machine learning potentials, and then they got some. So they used DFT. They used not these programs like WASP or Quantum Espresso to obtain some energies of the structures, but they used machine learning algorithms. And more generally, this program is we can formulate in this way. So we should find the global minimum of potential energy surfaces. So Alexandr also mentioned this potential energy surfaces. He showed some examples. So we have such energy landscape. In this landscape, every dot of this landscape is some structure. So when we see some dots on the hills, we can say that this structure are not so good. So they have a huge energy, and perhaps in nature we can't observe the structures. When we see this, minimums, so we can say that maybe the structures are rather good, so they can be stable or metastable. And we had somehow to find the global minimum. There are a lot of ways to do it. Or maybe you can see also this. So it's like, so we like took the shot from another point. So it's our potential energy surface. Then we have some structures. So here structure, here some structure, here some structure, and here is our global minimum. So we had to find this global minimum in some way. Evolutionary methods helps us to do it. So and helps us to do it in some reasonable way. But the problem is that usually we use DFT to do it, and we had to calculate a lot of structures, and most of the structures will be crappy. They will be really crappy because we should then combine them somehow and to get more or less reasonable structures, but most of structures will be bad. It means that we will spend a lot of time and a lot of computer researchers to calculate bad structures, and we don't need them in the future. So that means that it will be very good to add here some non-DFT method. And so this is what we have done with Bogdan. So we removed DFT in most of the calculations, and we added some force fields, and then in future we want to add some neural networks to it. And we also used atomic simulation environment. It's Python library to make this program. I think if you have if you work in some computations, maybe you have experience with ACA. It's very useful, and it's very wide tool to make some to create some programs based on crystal structure. So you can make some crystals. You can calculate, for example, here is example from their site how to calculate energy of hydrogen molecule. So it makes some steps, then it gives the potential energy, and so on. So it's very useful tool, and we used this tool to create our own code with for this evolutionary approach. So this is how it looks like it was one of versions. We wrote it on the blackboard in the Kyiv Academic University. It was cut because I wanted to place the title. It's so Bogdan Semenyuk, my student, he made this master's thesis about this. Here you see Bogdan's photo in Saxon, Schweiz. So he was here in 2021, and he was supposed to work with 14 Zona. And last time he launched 14 Zona in KAU, it was 23rd of February of 2022, and the next day it was Russian full-scale invasion in Ukraine, and then this 14 Zone was shut down, and then it was shortages with electricity, and it was not obvious that Bogdan can make experimental thesis, experimental diploma. And he asked me if I can give him some task in which he can which will allow from him some computational skills, and I gave him this task. So, and I think it was a perfect match. Bogdan named his approach like H, like ICE, Gauss, and Quantum Express. So we removed DFT from computationals, and we used Gauss. So Gauss is a rather old and rather simple program. It uses force fields like Buckingham or Lennard-Jones force fields to calculate the energy of structures. So this Coulomb energy gives us approximately 90% of total energy. So we thought that it should be some reasonable simplification to our calculation. So this is our algorithm. So we use ASE to create initial population of the structures. Then we use some calculators. So we use here Gauss, but potentially we can use VASP and Quantum Espresso. But we made it on a computer in Kyiv Academic University, not on supercluster. So we used Gauss, and just to boost time of our calculations. Then we calculate energy with Gauss. Then we also use ICE to take the best structures, to mutate them with some algorithms, and then we make this algorithm till we will find some interesting structures. And how to compare the structures? We have used fingerprint method. It is also well-known method. So here you see the formula and the main idea. So we take some atoms, and we take these circles, and we see how many atoms will be in the neighbor to this atom. And then we built this fingerprint function. So also we normed it because, of course, if we will make the circles, the number of atoms will go to infinite. We don't need infinite because it will be not possible to make such a beautiful graph. So we scaled it on some unit cells, some number of unit cells. And here you see some example. It's like we start from silica, and then we find, then we look for oxygen atoms in the neighboring as neighboring atoms to silica to silicon in some structure. And you see some it is the closest number of atoms, then scaled atoms on some another distance. So here is distance in angstroms, and here is the number of atoms. And this function should be unique for each structure. That's why we can compare them. That's why it's called fingerprint, because it's unique. And some tests of our approach. We used silica system as one of our test systems because it has a lot of polymorphs, and we can see if we can find all these polymorphs. So here are some results. It's at the end of the third generation. It is the initial population. We see that some structures, each dot represents the structure. So some structures has this energy minus 15 15 electron volts, and then a lot of structures has bigger energy. But they are more or less in the small interval, like 5 electron volts. Yeah, then after 10th generation, we see some bunch of structures which, so this is some good structures which has the lowest energy. And different colors means that we used different methods to create the structure. So it's like mutation, it's like crossover on some or random structure. 20 and 40. So at 14th generation, we have stopped and we see a lot of structures, you see. So a lot of structures here, and this is stable and metastable structures for this silica system. Here is fast diagram. Here are our results. So we didn't find only coesite because it has a lot of atoms in unit cell. So we didn't want to make such calculations. We just got this, and this in a few runs of our program. And here you see some comparisons. So the first line is was made from our program, and second line it's from a materials project database. So we had to compare it with something. So we have found quartz, beta quartz, tridymite, cristobalite, stishovite, and even more. So they are not on this phase diagram, but they are metastable, but fluorite, hydrophilite structures. So, and here is fingerprint function, cosine distance. If it is 0, it means perfect match. It means that we have found the same structure or almost the same structure as reference structure. And all this cosine distance, they was very small. So it means that it was it. So we made all energy calculations using Gauss. Then we took, at the end of the calculation, we took some best structures and recalculated them with quantum espresso because we wanted to add some quantum effects, not like Coulomb effects, but some quantum effects. And here is materials project MP, materials project from materials project database. And here we compared these fingerprint functions for different atoms like oxygen, silicon-oxygen, from this structure and this structure from a materials project structure. So it shows us perfect match. They almost ideally match these plots. Just another example for stishovite. It is 6 coordinated silica. So here this is 4th coordinated. So we have this tetrahedron as structural blocks, but here we have octahedron as structural blocks, and we also got the structure. It also matches good with reference structure. It's just, for example, in diploma we have a lot of dozens of pages with this information. Another system, Lanthanum 203, we wanted to see if it works with huge atoms, and it also worked. So we also got the structure after quantum espresso relaxations. We got almost the same structure as a reference structure. And then we used a bigger system. So it was magnesium, aluminium 204. So it has roughly 50 atoms in the unit cell. So it was rather huge system. And you see here, so these structures from materials project, these structures from our search, H1 means that it has the lowest energy, 2, 3 means they have higher energy. Here for this huge search, we didn't find exactly the same structures. We had find some good metastable structure. I think that the problem is that in this case, Gauss potentials are not good enough because they have some. So we stepped back in accuracy using Gauss, and I think that In this case, we see the result. We see that it is in some cases it is not good enough for example, this system to find exact match. But we have found a bunch of really good metastable structures, so they are very close in energy, the structures. So they not matches exactly, but they are really very close energy. So it works rather good, I think, even for such huge systems. And what's next? So the main weak point is Gauss. So we used it to accelerate the search, and it really works as accelerated tool, but it is not good enough in the point of view of physics. And that means that probably we will add it with some machine learning potentials, which use Olexandr Isayev. So we have collaboration with him. And probably it will give some fruitful results in the future. So thanks a lot for your attention.
Thank you very much for the interesting talk. Questions?
So basically your code sorry finds minima in some quite complicated energy bands.
Yeah.
How might we use a neural network? Do you use, I mean, one needs to first train neural network using some library of known answers of
Yeah. I want to apply neural networks here. So we create the structures using Python. So we have made this code to create the structures, to set them, but then in some way we had to calculate energy of the structures. And we used Gauss, we used Coulomb potentials to calculate it, but it's not good enough because it don't include some quantum effects like spins or some more interesting moments. And in this point, it is reasonable to change Gauss or DFT methods to machine learning. So it means that if we have pre-trained machine learning libraries for some elements, so we use these elements like silicon and oxygen, and then we use it and calculate the structures. So that's the idea.
neural network does not minimize the energy, just computes the energy.
Yes. So it just computes the energy of the structures which will be created by the algorithm.
All the structures you considered are insulators, is it correct? That all the structures you considered are insulators, not
here, yes, but yeah, we didn't check the metals here.
problem or
no, it's not a problem. It's just we wanted to find one system. So the idea was that one system has a lot of polymorphs like silica, then some huge atoms like titanium, and then some just huge unit cells. So it's not like metals or non-metals. I think that it's not a problem.
With you set symmetries of your random structures fixed, meaning that okay, at this step I take like 3 cubic structures, 2 hexagonal structures, like 4 tetragonal, and mix them up to other position. Or you don't set the symmetry at all, and then somehow.
We have faced the problem that ICE don't set symmetry in good way, in the way we wanted to do it. So we wanted to do it. We wanted to take some symmetry, then fill the symmetry with atoms and see what will happen. But now we have so we used not symmetry. So we can use some constraints. Yeah, we used not symmetry, but we used some volume of the cell, so we can approximate some reasonable volume. And then the sizes of vectors of the cell, but not the symmetry. With symmetry, it will be better.
I just didn't understand the answer for the first question, which Oleh asked you. What do you expect to see with this machine learning stuff? From composition to structure, the step?
From composition to structure, yeah.
The step from composition to structure.
Yes, yes. This is the step from composition to structure.
It should give you this.
It should give the energies of the structures, but we can calculate more or less precise energies with DFT, and it will take a lot of time. We can calculate not so precise energy with Gauss, and sometimes it can miss some complicated structures from physical point of view. And with machine learning, you saw the plot on Alexandr's talk. He showed that force fields like Gauss has the lowest accuracy and lowest calculation time.
This I saw, but and when you talk about when you call it potential, why you called it before potential? You said that it will help you to predict potential.
It will help me to calculate these energies, and these energies they create potential energy surface. Not potential, but this thing, potential energy surface.
So this is was misleading for me. I thought that with this you will get the effective potential of interaction.
No. It means. Yeah, it means that we can calculate all these energies, and these energies they create this potential energy surface. This was the question.
So these energies that you mean, these are enthalpies, or you also include temperature and enthalpy?
Not temperature now.
And pressure?
Pressure is possible.
More questions online? No? Then, yeah, thank you very much. Let's move on. And the final presentation will be given by Ihor Suhenko, who will present also a theory work on searching for superconductivity in apatites.
Greetings, dear colleagues. Thank you for this opportunity to present the topic. And first, I must point out that actually this project, this whole idea, is very recent and it's in the earliest stages. So I mostly present the idea and the motivation and some preliminary results. Right. So yeah, the idea is to, yes, it's indeed to look for the features of superconductivity in the crystal, in the family of crystals that it hasn't been yet reliably observed. But in order to justify it, I have to present for some reason why did we choose exactly apatites. And there are a couple of reasons. Several of them are chemical, some of them are historical, so to speak. And main reason is that the apatite structure is very resilient and robust when it comes to the substitution of chemical compositions. So to speak, like if this is the unit cell presented, which is has its hexagonal symmetry and this general chemical composition, basically it would be possible to replace all of these composing elements in a quite wide range of stoichiometry or non-stoichiometry, and then the structure will still keep the same. Then there exists quite a huge amount of data on those different types of substitutions, namely coming from medical and optical fields, and linear laser optics and so on. Last but not least, Professor Kambisky, whose idea was it initially? He himself has a great deal of experience when it comes to the structure and properties of the apatites. But why then superconductivity? Actually, most of you, I'm sure, have heard about this big news that came out last year about the supposed discovery of a room temperature superconductivity by the Korean group, which was named LK99. Yeah, so by 2024, after a huge wave of research, which you can see, it has been basically a consensus established that no, there wasn't any superconductivity in the samples, and the samples weren't even metallic for the most part. But the issue is, while this whole wave was ongoing, while it wasn't clear yet the answer, then a huge amount of research was produced, including the theoretical research of the exploration of the electronic structure of this model system that represented the LK99. And there, the idea is that it presented some features that, with the proper tuning of properties, could have actually lead to some form of superconductivity for several reasons. They have some important similarities to the existing superconductor families, and also they feature the flat bands near the Fermi level, which many systems do, but I'll explain later their importance. They bear some important similarities to the cuprate systems as well. So basically the idea is, taking the apatite crystal structure, can we tune the chemical composition in order to enhance those properties, or to actually tailor them? All right. And now to the question of the flat bands. Why are it was one of the features that initially, when nothing was clear about the LK99 story, was considered as interesting, as a point of interest. Why, like, theorists also delved into it at first. And yeah, basically, so when the flat bands cross the Fermi level, the density of states, on the contrary, it's diverse. Basically, it's very huge at that level, and it means that from the energy point of view, the system wants to open a gap, basically to lower its energy collectively, and in a way to organize in some next quantum structure. Basically, it can be superconductivity, charge density wave, or some or superconductivity as well. And from the BCS theory, it follows that in the limit of a flat band, the gap, the superconducting gap, its value should increase, meaning that with a given attractive interaction, the dependence would be such that it wouldn't be exponentially suppressed anymore. And the critical temperature is the monotonic function of the gap usually, and therefore the critical temperature should be also enhanced in principle. Yes, that's all fine and well, but then first I should remind you what was the issue, why from the theoretical point of view the famous LK99 didn't prove to be any kind of superconductor. It is necessary to kind of recap to understand the point of the idea. Yeah, so those flat bands on the Fermi level are great if they are actually there, because sometimes the strongly correlated effects in terms of electronic structure may actually lead to an opening of insulating gap. So this in this case, I'm talking about MOT or charge transfer insulating nature, which is, as it is known, is difficult to treat in terms of density functional theory, and this nature was predicted in the Oleh case with the help of more advanced methods like dynamical mean field theory, for example. Yeah, so the strongly correlated nature of, in this case, the copper 3D orbitals led to the Coulomb force overcoming the gain in energy from the conductance, and therefore the material became insulating. This figure that I showed, however, proves it with the DMFT, but they also showed that in case of this model system, by introducing doping, this mod gap can be closed, and we can bring back the conductivity as well. Yeah, so, and also this kind of behavior, like being a mod insulator and then becoming a metal via doping in some range, is also reminiscent of the high temperature superconductors as well. Yeah, there is also the framework of the specific theory of the flat band superconductivity that I will briefly talk about. So basically, the flat bands that I talked about, they might be absolutely trivial and just arise from the local separation of some states or some like orbitals in the crystal. Meaning that not all flat bands are equal and interesting from the point of view of superconductivity. And recently there was developed the theory to predict starting from the topological properties of the orbitals that create those bands. The idea is that this superfluid weight, which is like free energy per volume, and the quantity which is, if non-zero, basically guarantees the existence of a superconducting pattern. It was linked to the topological properties of the orbitals through the Chern number, meaning that if the orbitals that create the flat bands are topologically non-trivial, then it's already a necessary condition for the superconductivity to exist there. Meaning that if they are topologically trivial, then we can basically pretty much guarantee it's not there anymore. And further, the theory was improved for the multi-band systems and for time also symmetry broken systems and so on. And interestingly enough, the calculation of this parameter, which is called quantum metric and which is used to prove whether the superconductivity can exist or not in the systems, it was actually used by some papers, by some studies in connection to the LK89 problem. And the researchers kind of disagreed on some parts because one paper found it to be absolutely trivial, and the other, like using the different sets of parameters taken from different sets of DFT calculations and building tie-binding models with different coping parameters and so on, came to the conclusion that in some cases those bands might be non-trivial as well, and the value of this quantum metric increases if with the stronger hybridization of the neighboring orbitals. Yeah, and like also I need to show the band structure as well, but the thing is that oxygen and copper orbitals, they are coming very close into each other, and if touching occurs, then it's also beneficial. Anyway, the idea with those topological non-triviality is also linked to the real space localization of the orbitals as well, meaning that if they are very well spatially localized, then it's more likely to be trivial than not. Right. Also, when it comes to the treatment of the strongly correlated electron systems, where the Coulomb repulsion strongly outweighs, in this case, the bandwidth scale, there exists several theoretical approaches to treat those, and there are theories that even describe the emergence of superconductivity in those systems from a microscopical point of view. So basically, those two that I present here, in short, one treats the emergence of the superconductivity from weak repulsion and another from strong repulsion. And both of them were recently applied to the twisted bilayer graphene. First one explores the Coulomb-Luttinger model, which basically where the Coulomb potential, spin Coulomb potential in a metal has its oscillation, and then in case of non-zero orbital number, it might be attractive in some regions, and then pairing might occur. And the other one explores the formation of main body quasi-particles that when they are tunneling, they are kind of pushed closer to each other by the Coulomb repulsion, so to speak. And those are the frameworks that are not being explored quantitatively yet in application to our system of interest, but they might, the existence of such frameworks show that in the strongly correlated electron systems, there might exist all kinds of rich physics there. Another consideration is that in a way, this copper-doped apatite system might share some similarities to the coprate families, but not the coprates of YCBO type. If you're talking about the geometry of copper-oxygen coordination, you see the YCBO type and the layer structure, they host so-called corner shared geometry, which is presented here. But some systems, including quasi-dimensional systems, and as far as I remember, the one of the specimen is the strontium-calcium coprate, if I'm not wrong. There, the geometry is so-called edge sharing, and it means different angles between copper and oxygen. And in this case, well, the idea is that in YCBO type coprates, it is considered that the superconductivity emerges when the antiferromagnetic dop state is destroyed by doping, meaning that the undoped system is insulating and antiferromagnetic, and then a superconductivity emerges at some point. Here in the edge sharing system, the antiferromagnetism is heavily suppressed between the nearest neighbors because of specifically the geometry. Like the wave functions become orthogonal and they cannot order in such a way. Here the idea was this analogy based on this recent archive paper is that in these specific systems, those angles, edge sharing angles, are very far from 90, so their orthogonality is no more. So then the antiferromagnetic order might emerge again, and then perhaps like it also can be manipulated with the pressure, and the analogy with quasi-one-dimensional coprate systems become kind of a little closer. So there are listed several systems that share some analogies and similarities to the doped apatite systems. The first one, well, basically the similarity is the hexagonal system symmetry and strong Coulomb repulsion, strong correlated regime. The other one, just it's quasi one-dimensionalness, while also having hexagonal structure. Same as the next one. Yeah, this is bilayer graphene. Also, in terms of band structure and the correlation regime and this crystal symmetry and about the similarities. And this paper already presented pointed out like almost visually exact correspondence between the Fermi surfaces of the copper lead apatite system and uranium platinum 3, which is a heavy Fermi superconductor. Yeah. So there exists also a trick in terms of density functional theory. There exists a method of treatment of treating the strongly correlated systems via symmetry, crystal symmetry breaking, so to speak. So it was also recently applied to the cuprate HTC systems in a way to, like, it was first recently shown. Well, beforehand, in terms of DFT, the cuprates were mostly represented as metals, even though there were strongly correlated insulators, those that were actually in experiment. But there, this paper, they found that a correct solution which correctly approximated the experimental situation with the mod insulating strongly correlated measure can be represented by breaking of the crystal symmetry and then finding a solution. So basically, instead of unbroken symmetry and strong correlation, you have broken symmetry and normal correlations, but the resulting band structure and so on, it looks almost the same in terms of representation of the real picture. This approach was also applied to the LK99. It was one of the theoretical arguments that proved that it was not any kind of superconductor or metal. And this is what we based our preliminary study. So in order to explain the first results, I need to go back and just say that, well, of course, all those complicated theories are fine, but first, in order to have any superconductivity, you probably need to have a metal state. Your sample has to be a metal in the normal state, at least. And therefore, the preliminary steps that was considered in this search was to look for the stable metallicity in the next compound of consideration. So here, this approach of symmetry breaking was applied to the next candidate material that we decided to consider, the vanadate lead apatite with copper. Vanadate in particular was considered because of it was experimentally synthesized before and characterized also in the literature. Yeah, so then the discovery based on the density functional theory calculations was basically that in this case, even after the symmetry breaking, the metal state persists, meaning that the bands still cross the Fermi level. Of course, this is not a definite result because with those tricky systems, DFT may be misleading, as we know, but still, those are the first findings. And also, the difference between magnetic ordinance here becomes very, very small, meaning that in the experiment, it would probably constitute some kind of paramagnetic system, but by replacing from the point of view of crystal structure, by introducing vanadium, we would be replacing those atoms in the tetrahedra. And in this way, we completely change the geometry of the copper oxide networks in the system. And this change in geometry is what causes the change in the electronic structure. Meaning that, so the energetic costs of different magnetic ordering changes as well. And the opening of the gap at the Fermi level may not be already energetically preferred in this case. Next, we try to explore the possible whole doping by selenium, because selenium-4 has a lower valence, and to introduce the whole type charge carriers in the system, but by modeling it as in such high amounts of doping as 1 per unit cell, we decided to observe that distortion of the crystal structure caused by the introduction of selenium outweighs the possible extra charge carriers, and the system stays insulating again. So doping with 1 whole per unit cell doesn't bring it anywhere to the metal state. Yeah, so to summarize and to give the perspectives of this idea for the future, we are also, of course, considering the experimental synthesis, and here are all the plans for the future. And then, of course, with the experiment, there are a lot of challenges, and much more than the theory. Actually, the biggest challenge is the correct and consistent and predictable realization of the crystal structure, because in this unit cell that I showed, the dopant metals can enter different crystallographic positions, and actually it changes a lot. So those are in the hexagonal symmetry. It's like the nomenclature is 4H and 6F Wyckoff position, and only the 4H is considered of the importance for those kinds of applications. And yeah, so there is a problem of controlling exactly the stoichiometry and the crystallographic positions of the doping atoms. And yeah, that's why it's highly required to come up with more predictable methods, synthesis methods, than were used already in the literature. But as well, there are ways to tune those distributions chemically while replacing one or the other constituents. Yeah, so in final words, I would like to present the team members that collaborate. We are from Institute of Metal Physics. So the team is composed of the Department of the Physics of Nanostructures, led by Professor Krubivsky. And of course, with support from friendly Kyiv Academic University. And so to complete the project for this idea, we actually recently won the funding of the Ukrainian National Research Foundation for this specific quest for superconductivity. And well, my conclusions basically I already said that those systems present a rich playground and kind of a construction set for tuning, tinkering with the properties that might eventually lead to the superconductivity, but it's quite a daring and monumental task to achieve. Still, I hope we'll learn a lot in the process, and of course, we are very much open to the collaborations and suggestions. And with this, I'd like to thank you for the attention.
Thank you very much for your talk. Questions? Too much information is for me, but let's say, so you have these crystals, okay, 99. Yeah. Did you try no superconductivity? I understand there is no, but the diamagnetic response. Is it diamagnetic? Do you see it?
There were a lot of papers that tried to measure it. We haven't really obtained them yet due to the technique. Unfortunately, no, not yet.
That crystals are not the compound.
Which ones? No, something else. So
then from summary of what is in the literature, the predicted electronic structure is predicted that it's rather flat.
It is not the case, or it is no, it was not.
Yeah, it is the case, but it is the case. But the problem with particularly the LK99 is that it turned out in actually to be insulating in the end due to the strongly correlated effects. So here the idea is that change another composition, try to find another composition where it would not happen, and those flat bands will stay at the Fermi level.
So in DFT calculations, it is metal, but in reality, it is.
Yeah, basically yes.
It is insulated.
Yes.
And so this, just picking this up, this composition that you investigated, is it kappa 2 plus?
Yeah.
So it's stoichiometric kappa 2 plus.
No, well, in the experiment, yes, kappa 2 plus.
Because then it's very unusual. Like if you have a stoichiometric system with kappa 2 plus and you apply some U in the plus U scheme, then I think you always get a gap.
But there people couldn't, and it was also one of the points that led to the interest initially. So yeah, of course everyone applied U from the beginning, but initially like everyone got the metallic stain. Me too. I repeated the calculations as well. And same.
And this band that crosses the Fermi level, it's a copper band.
It's copper 3D with hybridization from the neighboring oxygen to the orbitals.
It is copper dot or copper based? How much copper is it?
One per unit cell, but the unit cell is 41 atoms. So one per unit cell, but the unit cell is 41 atoms. Meaning that there are in the non-doped case, it's 10 lead atoms, and in the doped case, one of them was replaced by one copper. So 1 to 9 if we take the metal. So in the chemical formula,
shown some case where there is this copper chain somehow.
Yeah, it was here. Yes, yes. I'm sorry. It's a different one. It's actually with a larger amount of copper models in the system. Like either 2 or 4 per unit cell. Yeah, and it's just pure theory as well. It hasn't been synthesized.
I just do not understand how to speak about copper band if it's not much copper.
Well, but it's there.
But here there's a lot of copper atoms in this cell.
No, I mean okay.
So
still, I would say like I mean, not much if we take the whole unit cell, yeah, which is 41 atoms. But if we like, in terms of replacement, it replaces one of the lead positions, and they're only 10 per unit cell. So it's visible. It's pretty visible in the density of states too. So it's not that it's 1 per 1,000 or something. It's still there. And speaking of calculations, in addition to the plus U thing, I also tried with the scan function, if you heard of it. Also Fermi level thing. But then with the symmetry breaking and with the more advanced theories like the DMFT, they were able to show the gap. So yeah.
Just on the DFT level, if you do structure relaxation or you calculate forces, you get a reasonable, reasonably converged structure. Very strange. Yeah. More questions? Seems not to be the case. Also online? Yeah, then I think we close the session and thank all the speakers.
When we show for finish